it goes. Now I am. Thank you very much, Angel. Yeah, the green border. Alright, well, I'm just going to have to splice something in here. So anyways, as I was saying, we've done a fit before. And also, a fit equation, the the things that the factors, so in our case we do straight line fits. So we have a slope and a y-intercept. These things end up either one or both of them, one or both, are physical quantities. And that's when I told you we were going to do a fit, that was the whole point of it. We did the fit because that was the only way we could determine something. Oh, and Ashley too, thank you. Yeah, I'm not recording to Zoom. I'm recording locally because I was saying earlier, even when I say in Zoom record to my computer, it actually goes to their server and back. So any glitches that the internet adds are still there even when I record to my computer in Zoom. So I'm using this thing called Camtasia locally, but as you guys pointed out, I wasn't even doing that, but now I am. When we're going to do an interpolation, and in our case we're going to use we're going to look for quantities non-physical, and they're called coefficients, non-physical terms. There we go. And there's nothing wrong with that as long as you're only working within the actual data you have. And then this is, once we get through with the background, we'll spend a lot of our time doing this in the spreadsheet. Oh, and for the latecomers, please make sure and go to the Canvas homepage. And there's two Excel files there. One about Physics 1200 BP data and Physics 1200 EKG data. So we especially need today the BP data. And I believe, yeah, so continue the concept of interpolation. But first I want to make sure everybody's gotten, is it okay for me? Well, I know, I'll just go to page 3 and you guys yell at me to go back if you need me to. And I'm looking at the chat. I finally realized after 3 semesters you guys can't see this chat window. Because I'm always telling people that if you're afraid to tell me you don't understand something, that the other people might see it. Because I assumed you would see this chat window because I'm sharing my screen, but apparently you don't. Okay, so part of the interpolation process is we going to do a little data quality, and it's basically we're going to look at the data and we're going to make some qualitative judgments about cutting some of it out, getting rid of data that could fool the interpolation, and you'll understand that more when we get to it. So again, oh no, not again. So our interpolation is, instead of using the y equals mx plus b, we're going to use what's called a polynomial. We're going to do a polynomial fit. And a polynomial fit just means that, in fact, let me write it out better than this. There's a1 x2 no, a sub 0, excuse me, x to the 0 plus a2, a1 x to the 1 power plus a2 x squared plus a3 x cubed. Right, so we're going to do a 4-term fit today. And then, but of course, it can go to infinity. So however high we want to go, whatever we can decide to use more terms. And the a's can be positive or negative. Oh, I wrote it right. Well, ABCs. Or a negative. I had a little brain fart the other day when I started using ABCD. It's supposed to be like this. Now it turns out, with a polynomial fit, you can create a fit line that'll fit anything. But the coefficients, the a's, are not physical. Even though the x's will be physical, like the time, in today's case it'll be time, but the other day it was voltage or current. The a's themselves, the coefficients, are not physical quantities. And so these things are notorious because they're very tempting. You can fit any shape, but as soon as you try to extrapolate, they go nuts. They just make the craziest graphs. So you cannot extrapolate with a polynomial fit. But in our case, you'll see that we don't care about that. And sometimes we do polynomial fits with only a few terms, because if you can imagine, if you remember physics 1100, this looks a lot, if I go up to x squared, this looks a lot like the kinematics equation, where you have x equals x sub 0 plus v of x 0 times t plus a of x t squared. So this is a polynomial. You don't even realize it. That's a polynomial. And so x sub 0 would be my a0, and v sub 0 is my vx sub 0 is my a1, and the acceleration is my a2. And so sometimes, if we can sort of shoehorn into a polynomial some physical quantities, and we can use it to test for different fitting equations. If we can't think of a fitting equation when we look at new data, we sometimes will use polynomials to help us to decide what our actual fitting equation should be. But in general, they're only good for interpolation. And then, of course, I've got this little orphan down here. And this is going to be for the EKG. So we're not going to look at this today. We'll look at it when we come back. Okay. I just wonder why the mouse cursor is flashing. Just turn off the tablet for a second. Still flashing. Huh, don't know why. Alright, so I just found this video today. So it'll get the logical buildup is going to get a little choppy. I couldn't decide when was the best time to show this, but it's really important for understanding how our device works. So let's see if this will run without. Oh, wait a minute. I have to. Can I pause that? Because you can't hear the sound. Record, share sound. Okay. So here we go.
Systole and diastole. Systole and diastole are two terms that you'll hear about the heart. Sometimes you can think of systole as the work of the heart. Systole is when the heart is squeezing the blood out to the rest of the body. And you can think of diastole as the blood coming to the heart when it's totally relaxed and the heart's filling back up, getting ready to squeeze the blood out again. It reminds me of one of my mentors whose house I went to, and as you're entering the gate it said diastole. As you're exiting the gate it said systole. So I guess we can think of systole as going to work and diastole as resting. It also correlates with the blood pressure. The blood pressure is highest during systole because that's when the blood is squeezed out of the heart in a bolus fashion, and you measure the blood pressure in the blood vessel, it's the highest blood pressure at that time.
So keep in mind, watch that the way this artery is flexing. That's important to understand how our detector works.
In diastole, that's when the heart is actually resting. It's not pumping the blood out, and at that point the blood pressure is the lowest possible in the blood vessel, and that's where you get your diastolic blood pressure, sometimes called the lower number in the blood pressure.
Oops. Yeah, I'm muted just in case my speakers were feeding back into the microphone here, and you were hearing echoes. Okay. Now, so let's take a look at this guy. Come on. Okay, so the way our detector works is we pump up and it bleed. We don't press any button. It has a controlled bleed of air, and you start to see something, and then you start to see more, and then you start to see it fade away. Now, this little guy up here in the upper right, this is the ideal, sort of an ideal situation. And if you could assume that we could pump up the cuff and set it at the average pressure, we would see this shape. But our system can't do that. So yeah, pump up the cuff. We can, at some point we can see this. So this is when the ventricles pump out, and I'm still not I'm not sure if this is true, if this is the atrial contraction, because that would be, when the atrial compress, I think, should bring down. Yeah, I'm going to get rid of that atrial. I still haven't had a good explanation of this thing. But what we do know is this is when the ventricles, the two main chambers, give their push, and then down here is when it's resting and it's about to start over again. And you see this note I put here, and it's in the lab manual too. It would be interesting if we could pull this out of figure 5, and that's what this is up here. And this is my big revelation over the weekend. Oh yeah, and by the way, the units are millimeters of mercury. And that comes about because of the original barometers. You take a glass tube and you fill it with mercury, and you have a bowl full of mercury, and you put your thumb on this thing and you stick it in you turn it over and then put the end into the pool of mercury, and then take your thumb off. You need about a meter of glass tube, maybe a meter and a quarter. And the mercury will drop down, but it won't just come out completely because the atmospheric pressure is pushing on the pool of mercury. And up here in this space, the pressure is equal to 0, which is really hard to wrap your head around. And 760 millimeters, so the pressure of the atmosphere is the difference between the level in the pool and the level in the tube. And this was what happens in the old style blood pressure uses mercury in a similar fashion. And FYI, Galileo, it's Torricelli that made the first mercury barometer, but Galileo, for fun, made one out of water. The thing is that the glass tube for water has to be 33 feet high because it's so much less dense than mercury. Okay. It's also why when you see hand pumping wells, they can only suck water up 33 feet, and that's that. They can't suck anymore. So the units, millimeters of mercury, we see this sort of thing, and it sort of disappears. So what we need to do now, and this is why I showed that video, we have to think about what is going on here. And so, is this camera the way to do it? Yeah, maybe. Okay. So when we pump up the cuff, this thing squeezes the artery in our forearm, in our upper arm. And in this case, you can still see a little daylight on the ends, but just imagine it's all the way up. And then in the case of like the manual, the old style, you're letting pressure down. And then your heart is beating, and it's trying to open this, but the cuff is holding it closed. And then all of a sudden, the heart is just about able to push it open slightly. And that's the first sound. And that's the systolic pressure. Again, you're making believe that the two ends are closed also. So we're only focusing, in the case of this little piece of rubber tube, we're only focusing on the center of it. So just as the heart is just able to make it open, that's our high blood pressure, our systolic. Now, as the pressure drops, the heart is able to open it some more. But it's still, as the heart pressure drops, it still closes all the way. So you still hear the Korotskov sound. At some point, the cuff is now, it's squeezing it so that the heart can open it, and as the blood pressure goes down to the diastolic, it barely closes. And then you let the pressure come down a little bit more, and it never closes. And then the Korotskov sound disappears. But in our case, the pressure cuff is still telling us a pressure, and our arm is still flexing, but the lowest pressure is no longer here. So we have to find a place where the swing that goes down below, the average pressure, is the maximum, because that's the point. So the pressure in the cuff, no, the pressure, let's assume the pressure in the cuff is constant, and it's just at the diastolic. So my heart pumps, opens, the heart relaxes, and it just barely closes. So at this point, we're seeing the maximum amount of swing coming out of the pressure cuff. Now we're at this point, and the heart's making it move, but it's no longer closing, so we're not going to see quite as much of a swing. Because even when we're not closing the blood vessel, your arm is still swelling as the heart pumps. So historically, what we've done is we've looked for whenever the blood pressure, you see the beginning here, that's the easy part. But how do we decide the bottom part, the lower pressure? Because we don't, you see that it's still there. So historically, we've just sort of said, all right, let's look for this shape. Because we don't have a way, two things are going on here. First of all, the ideal situation would be if we could set the cuff at the average pressure, but it would still have the ability to keep squeezing. So when the heart is at the average pressure, it's open, and then as the heart relaxes, it just closes, and then when the heart beats, it opens, but the cuff, like my fingers, are still touching, and I can still read the pressure. But it turns out that, and I did a study, the range of the detector is only about, when I zoomed in, it's only about plus or minus 5 millimeters of mercury. And we need to see a difference from the systolic to the diastolic of 60, about 50, 40, 50, 60, maybe even more. So we can't simply, I tried it. I tried pumping up the bulb so that I could see something like this, and it's not possible. So the thing that we'd really like, though, would be to have a way to produce the average, a line of average pressure here, and then we could subtract that from the data, and then we'd end up with something that looked like this. And that's the revelation I had. And I'll talk more about that when we get to it. And let's think about this. You know what? I'll talk about this later when we've gone through the exercise. So you already saw this. Okay. So again, that's the outline of what we're going to do today. We're going to do the digital sample, explore the digital sampling rate. Then we're going to take a set of data like this, and we're going to do a polynomial fit to do a sort of average pressure, and then we're going to subtract that from the data, so then we can focus on looking for a figure of merit, which would be the lowest possible swing right here, and or another would be to see this nice shape. Okay. So here is the basic idea.